Hi, this is John Whitaker again for the Mathematical Analysis 2 class. This is our third video lecture, and we had finished last time, going a little bit over, but finished with algebraic combinations of differentiable functions. We had also earlier shown that the derivative of a constant was 0 and that the derivative of x was equal to 1. And I'd like to start off with using those algebraic combinations along with the two facts I just mentioned to say something about the derivatives of polynomials and rational functions. So, since we have proven that the derivative of a constant function is 0, and the derivative of f of x equal to x is 1, then the previous theorem about algebraic combinations of differentiable function gives us that all polynomial functions and rational functions are so all polynomial and rational functions are differentiable, except for x values where the bottom is 0. Okay, next thing I want to do is look at the chain rule for differentiation, and here's what it says. It says, suppose f is continuous on the closed interval from a to b, f prime of x exists at some point x element of a to b. G is defined on an interval I, which contains the range of f G is differentiable at So G is differentiable at f of x, and well, we'll just stop there and say if h of x equals to, or h of t is equal to G composed with f of t, then h is differentiable at x, and h prime of x is equal to G prime evaluated at f of x times f prime evaluated at x. So this is the chain rule. Okay, so let's look at its proof. Okay, we're going to assume the conditions here. Let f be continuous on A to B. F prime exists for some x element of the open interval from A to B. Well, it's the closed interval. G be defined on I, which contains the range of F and G is differentiable at f of x. We're going to let h of x or h of t be defined by by g of f of t. Then the derivative evaluated at x will be equal to the limit as t goes to x of, it would be g of f of t minus g of f of x all over t minus x. And that's equal to the limit as t goes to x of g of f of t minus g of f of x all over, and I'll rewrite this as f of t minus f of x times f of t minus f of x all over t minus x, where I have really introduced this f of t minus f of x in both the top and the bottom, so that's just multiplying by a funny looking 1, and then rearranging the fraction slightly. Now this will be equal to the limit as t goes to x of g of f of t minus g of f of x all over f of t minus f of x times the limit as t goes to x of f of t minus f of x all over t minus x, and that's equal to the limit as t goes to x of g of f of t minus g of f of x all over f of t minus f of x. And this other limit here, that's nothing more than f prime evaluated at x. I can do the limit of the product as part of the limit provided each limit exists. One of them we knew exists. What we need to do is show that the limit as t goes to x of g of f of t minus g of f of x all over f of t minus f of x, that's equal to g prime evaluated at f of x. Let me write that down. We will show that the limit as t goes to x of g of f of t minus g of f of x all over f of t minus f of x equals to g prime evaluated at f of x. And the way we'll do that is using the definition of the limit of a function. So we'll let epsilon be greater than 0 be given. We need a delta bigger than 0 such that for all t element of a to b with 0 being less than the absolute value of t minus x being less than delta, then g of f of t minus g of f of x all over f of t minus f of x minus g prime of f of x will be less than epsilon. So we're looking for this this delta. Okay. Well, since g prime of f of x exists, then there exists delta, or well, I should say then, the limit as y goes to f of x. So we're thinking about this limit in I, where g is defined, the interval for which g is defined, of g of, it would be f of, or g of y minus g of f of x all over y minus f of x. This guy exists. And so, and it's equal to g prime of f of x. So, there exists this delta sub 1, using the definition of limit here, greater than 0, such that for all y's element of I with 0 less than the absolute value of y minus f of x is less than delta sub 1, then the absolute value of g of y minus g of f of x all over y minus f of x minus g prime of f of x will be less than epsilon. Okay. Since f is continuous, on the closed interval from A to B, there exists a delta bigger than 0 such that for all t element of A to B with the absolute value of t minus x being less than delta, then the absolute value of f of t minus f of x will be less than delta sub 1. That has to do with the continuity of f, really at x. And so, what we're getting then is, thus for all t element of A to B with 0 being less than t minus x being less than delta. Okay. So we're in this situation, and that means that we know that f of t's output values for f are very close to delta sub 1. So that means that we're really in this situation, and that implies this occurrence. So the absolute value of g of f of t minus g of f of x all over y minus f of x minus g prime of f of x is less than epsilon. And that's exactly what we need to show. So the limit as t goes to x of g of f of t minus g of f of x all over f of t minus f of x, that is equal to g prime of f of x So what that says is that h prime of x will be equal to g prime evaluated at f of x times f prime of x, and that's what we wanted to show. What I'd like to do next is use this fact by looking at an example. And so we'll consider, this is straight out of text, we'll consider the function f of x equal to, it's a piecewise defined function, it's equal to x squared times sine of 1 over x. And that's what it is if x is greater than, or if x is different from 0. And it's equal to 0 if x is 0. So, where r as the usual metric. That's what all of our cases are right now. We will find f prime of x. Well, using the product rule quotient rule, chain rule, I should say, quotient rule, and a fact. The fact that the derivative of sine of something, let's say x, is cosine of x. Then, for x is different from 0, f prime of x is going to be equal to, okay, use the product rule right on the first guy, that's x squared times the derivative of the second guy. Well, the derivative of sine of something is going to be cosine of the something times the derivative of something. Using the quotient rule here, what we get is minus 1 over x squared. Then plus, now I'll write down the derivative first, that's 2x times sine of 1 over x. And so, simplifying that, we get f prime of x is equal to, it's minus cosine of 1 over x. Sorry, it's minus cosine of 1 over x. Plus 2x sine of 1 over x. Now, for x equal to 0, what we'll do is we'll use the definition of the derivative. And so we have f prime of x will be equal to the limit as t goes to, in this case, 0. Let's make it 0. It would be f of t minus f of 0 all over t minus 0. And that's just equal to the limit as t goes to 0 of f of t over t, which equals to the limit as t goes to 0. F of t would be equal to t squared times sine of 1 over t all over t, which is equal to the limit as t goes to 0 of t times sine of 1 over t. we'll claim that the limit as t goes to 0 of t times sine of 1 over t equals to 0. And so here's the proof of the claim. But we'll do this with the definition of limit. We'll let epsilon be greater than 0 be given. We need a delta bigger than 0 such that for all t, element of r with 0 less than the absolute value of t minus 0 less than delta, then the absolute value of t sine of 1 over t minus 0 is less than epsilon. So we want the absolute value of t times sine of 1 over t to be less than epsilon. Okay, the sine of 1 over t, for t value is not equal to 0, that's defined. For sine of 1 over t bounces between minus 1 and 1. And so what we get is, note that t sine 1 over t is going to be less than or equal to t inside absolute values. So, just restating, t times sine of 1 over t inside absolute values is less than or equal to the absolute value of t, which equals to the absolute value of t minus 0. And so we want this one to be less than epsilon. Well, let's let this be less than epsilon by letting, so let delta be equal to epsilon. Thus, when when absolute value of t minus 0 bigger than 0 is less than delta, then this t times sine of 1 over t minus 0 will be less than epsilon. So that says that the limit as t goes to 0 of t times sine of 1 over t equals to 0. Thus, f prime of 0 is equal to 0. So this was an example of a function that is differentiable everywhere. And what we get is f prime of x as a function to be thought of as minus cosine of 1 over x plus 2x sine of 1 over x, and that's with x being different from 0, and 0 if x equals to 0. What I want to point out about this function, though, in addition, is that note f prime of x is not continuous at 0 itself. And that's the reason is that as one of the reasons that the limit as x goes to 0 of cosine of 1 over x does not exist. next we're going to start working with some of the facts that we've learned from calculus, especially pertaining to having a local max or local min, and it associated to a derivative. So here is the definition. It says let f be a real function defined on a metric space X. That's a very generic definition. It says, we say, part A, F has a local max at a point little x if there exists a delta bigger than 0 such that f of x is going to be greater than or equal to f of q, and that's going to be for all q with the distance in the metric from x between x and q is less than delta. Follow-up definition, similarly, would say F has a local min. Minimum at a point x if there exists a delta greater than 0 such that f of x is going to be less than or equal to f of q for all q with the distance given by the metric in x between x and q being less than delta. As an example, consider function f of x equal minus x minus 2 to the squared plus 3. Then f of x has a local maximum at x equal to 2. And this can be seen graphically. If we draw this function, this is a parabola that is going down, and its vertex is going to be 2, 3. Okay, and when at x is 0, I'm going to get minus 1. It's 4, I'm going to get minus 1, so it's something like this. And so we can see that if I let delta be equal to 1, then about the value 2, I just look at this input values. It's definitely the case that this number of 3 is the highest output value that we get over that region. It needs to be a local max. Okay, next thing we want to do is list the theorem. And it says let f be defined on closed interval from A to B. And it says, okay, if f has a local maximum at a point x element of A to B, and f prime of x exists, then f prime of x had to be equal to 0. Okay, let's look at its proof. Okay, so we'll start off with the conditions. We let f be defined from A to B. And let f have local max at x element of A to B, and f prime of x exists. Since f of x is a local max, a local maximum, well, that means there exists this, we'll call it a delta sub 1 greater than 0, such that f of q is going to be less than or equal to f of x. And that's for all q element of A to B with the absolute value q minus x being less than delta sub 1. What we're going to do is we're going to choose I'm sorry, there's a slight mistake in my theorem. I need to go back and rewrite something here. Let's go back. Okay. The x here is not in a closed interval, but rather in the open interval. So f defined in the closed, but x has got to be in the open interval. What we're talking about for this situation. Okay. Okay, so what we have written is correct. What we're going to do is choose a smaller delta possible. So here we choose, or we let delta be equal to, here, the minimum between delta sub 1, the absolute value of A minus x over 2, and the absolute value of B minus x over 2. And here, these values can't be 0 because we know, after I made a change, that the x is in the open interval, meaning that x cannot be equal to A or B. So this distance, we're listening to top can't be 0. So we let delta be that point. Okay. Then f of q will be less than or equal to f of x for all q with the absolute value of q minus x being less than delta. What this does, it essentially removes the ability for q to be being equal to either a or b. Okay. Now, thus, when we look at all the x minus deltas that are sandwiched between a and x plus delta, which is definitely less than b, yeah, that's a restriction that we have, as I said, about delta. That's what's happening here. So our delta is such that it's centered about x. We're getting this neighborhood about x, and it can't stretch out to either a or it should have been b. Now let's look at certain parts of this inequality. Particular, so if we look at the x minus delta and look at the t's in between it and x, so these are like our q's, but we're only talking about the q's that are to the left of x. Then what we have is f of t is definitely going to be less than or equal to f of x, because f of x is this maximum. So, f of t minus f of x, we're taking the smaller one minus the bigger one. That's definitely less than or equal to 0. And t minus x, remember the t's that we're taking are to the left of x, so x is again bigger. This got to be less than 0. So, if you take a look at f of t minus f of x, all over t minus x, that's a non-positive divided by a negative. That's definitely got to be got to be greater than or equal to 0. Okay? It's like two negatives. Okay. What that implies is that the limit as t goes to 0 of f of t minus f of x all over t minus x, that has to be greater than or equal to 0. So, that says that f prime of x has to be greater than or equal to 0. Now remember, our goal is to show that f prime of x is equal to 0. And the way we're going to do that is show that f prime of x has to be greater than or equal to 0 and also has to be less than or equal to 0, so therefore it only has that it must be 0. Okay, well, we had looked at the t values, if you will, that were just a little bit to the left of x, but within our neighborhood of interest here. So what we do now is considering x less than t less than x plus delta, this part of the neighborhood, we still have that f of x is the local max, so it's the biggest value. So f of x is going to be greater than or equal to f of t in this region. So what we have is f of t minus f of x is going to be less than or equal to to 0. And t minus x in this situation is going to be greater than 0. So that means that f of t minus f of x all divided by t minus x. So this is like a negative divided by a positive. So this is going to be less than or equal to 0. It's not quite what I said, but it's close to that. So what that says is the limit, that implies that the limit as t goes to x, and this should have been t going to x, I don't know why I said that, of f of t minus f of x all over t minus x, that has to be less than or equal to 0. So that means that the limit as t goes to x of f of t minus f of x all over t minus x has to equal 0, but we know this limit is really equal to f prime of x. So that concludes the proof. In the proof, there were some details that I didn't go through, kind of substantial, but it's something that I'd like for you to look at. And that is, in particular, if the terms are always greater than or equal to 0 of an expression, and you take a limit of that, then what the output of that limit is, provided it exists, has to be greater than or equal to 0. That's something that you can prove by contradiction, and I'll ask you to look at that in our first set of problems. Okay, a very similar statement to what we just had can be made, and I'd like to write that on the board, and that is, here, if we let f be defined on the closed interval from a to b, such that, and if f has a local minimum at x, and here it's in the open interval from a to b, and if f prime of x exists, then f prime of x has to be equal to 0. This is a problem whose proof will be homework assignment for you. So this is left to students to prove. But it works very similar to what we had in the previous theorem. I'd like to conclude with some examples. What these past two theorems are telling us is if you have a local max or local min in this situation, where the function is defined on a closed interval, but the local max or local min occurs within that open interval, and the derivative exists, the derivative has to be 0. But if we consider the following examples. Consider f of x, the previous problem we had, equal to minus the quantity x minus 2 to b squared plus 3. We see, if we define it on, let's say, from 0 to 5, okay, then f of 2 equal to 3 is a local max. That's what we saw. And if you notice, the f prime of x in this case is going to be equal to minus 2 times x minus 2 to 1 less power plus 0. And so that derivative exists everywhere in 0 to 5. And so if we set that equal to 0, we get minus 2x plus 4, and that says that 2x is equal to 4, or that x is equal to 2, and that's where we did have the local max. Okay? So that illustrates that past theorem. Now let's consider another example. Okay. For f of x equal to the absolute value of x on, let's say, minus 1 to 1, then we can see very clearly from this graph that we have a local min at 0, okay, but f prime of 0 does not exist. So just because you have a local minimum doesn't mean that the derivative is equal to 0. In that theorem previously that I'm asking you to prove, it's analogous to what we did prove just a minute ago for local maxes. Here, we assume, in that theorem, we assume that the derivative did exist. Here was an example where it didn't. We still have local min. And then as a final example, if we consider f of x equal to x to the third on minus 1 to 1, then f prime of x will be equal to 3x squared, and f prime, the value of x 0 does equal 0. But f of 0 is neither a local max or local min. This can be seen graphically. I'll do it here. The x cubed function looks like this over this spot. And even though the derivative is 0 at 0, we don't have a local max or local min. So just because the derivative is 0 doesn't mean we got a local max or local min. That's enough for lecture 3, and we'll start with lecture 4 later. Thank you very much.